Well, thank you everyone for inviting me to be here. I'm very happy to be here. I just wanted to give you a brief introduction of who I am. I was also invited by Norm Cook last year to attend, so thank you, Norm. And I have a degree in physics from the University of Missouri and a degree in electrical engineering from MIT. I spent most of my professional career as an electrical engineer, and during that same time very much interested in physics as an independent researcher. So that's who I am. Let's look at the paper. I have a lot of similarities to Ito's work, and again, some differences, and I think that'll become apparent in the course of my talk. So I want to give a brief introduction to the nuclear force. The nuclear force is that force which binds the nucleons together in the nucleus. There is some popular theories. One of them is very good. Okay, one of them is the liquid drop model, which probably most of you are familiar with. And it uses the Weizsäcker formula, which, again, each nucleon bonds to its nearest neighbors. And it uses 5 variables in order to reproduce the binding curve. It's just mathematical curve fitting. There's no real theory behind those 5 variables or how they were selected. It's just mathematical curve fitting. Then there's the cluster model. Now that one is interesting because it is based on the alpha cluster model from the 1938. And there is a lot of active research going on right now with regards to the cluster model, particularly experimental and theoretical. What it says is there is structure in the nucleus. As we are all saying in this segment of our talks this morning, there is structure in the nucleus. And the alpha particle is the predominant structure, the predominant building block. The cluster model states that we end up with a chain-like structure. And they have seen this experimentally. When they look at the nuclides, they look like chains, links of alpha particles linked together. Very interesting model. Then there is the shell model, which was developed in 1955, which is an independent particle model. The particles are inside a well, banging around, and they don't interact with each other. Then the last one I want to talk about is the residual chromodynamic model, which is accepted now as the valid theory, mainly because it depends on quarks. None of the other models do. This model depends on quarks. However, the problem is that it's unproven mathematically in terms of being able to computer simulate what it might predict and comparing it to experiment. And the reason is because it's just too difficult to simulate each and every quark with the Schrodinger equation. I wanted to talk about quarks. Some of you may not be familiar with quarks. They were discovered or theorized in 1964, and then they've since been proven to exist. They are known to exist. The interesting part about quarks is they have a fractional charge, and you can see this right here in the up quark. There are only 2 quarks that exist in stable matter, and that's the up quark and the down quark. Now the up quark has a fractional charge of 2/3 the charge of a proton, and the down quark has a fractional charge of -1/3 the charge of the proton. This is what a proton looks like. This is what a neutron looks like. Now the residual chromodynamic model states that there is a force that binds these quarks together in a nucleus, and that's called the chromodynamic force. The residual force is that force which exists outside of the nucleon, such as this region here, and that residual force is what causes these two quarks to bond together. When those two quarks bond together, subsequently you have the two nucleons bonded together. And the residual chromodynamic force implies that this is the bond that holds nucleons together. This residual bond right here between the internucleon quark to quarks. Last year during the poster session, I showed a very good deviation of this residual chromodynamic model, which was based on, rather than being a blue quark bonding with a red quark, that what was going on was it was actually a down quark bonding with an up quark. And that made the difference. And I was able to do a very simple calculation in an Excel spreadsheet for all the nuclides and predict the binding energy very closely. Now that begs the question, what if that force here, rather than being chromodynamic, is electromagnetic? And that's what I'll be talking about, is the electromagnetic model. And I say that it is an internucleon quark-to-quark bond. It only bonds to the nearest neighbors. And this quark-to-quark bond is electromagnetic, not color dependent. And as you can see in this diagram, I have a proton and a neutron. And what holds those two nucleons together is the electromagnetic force right here between the up quark and the down quark. Now, one thing I should mention is that all of the charge in a nucleon exists in the quarks. There is no charge that is distributed throughout the bulk of the proton or the neutron. All the charge resides in the quarks. Similarly, that is where the magnetic component comes from. All the quarks have a very strong magnetic field associated with them, magnetic dipole. The up quark, if the magnetic field of the proton is got a spin with a spin up, the up quark also has a spin up magnetic dipole. The down quark would have a down magnetic dipole, hence the names for the up quark and the down quark. So if we look at this electromagnetic model, what are the equations that we can use in order to simulate this model on a computer? Well, you're all familiar with I hope you're all familiar with the electric energy. Looks like this equation here. And if I have a configuration of charges in any kind of random three-dimensional space, what you do is you do a double summation of each of these energies here, and you get this equation here. So you sum the energy of one charge to another over all the charges, and that will get, excuse me, that will get all the Coulomb energy. That automatically accounts for the Coulomb energy, and I am accounting for a charge over here to its nearest neighbor where the bond is, and as well to a charge that might be fairly distant, because I'm taking that into account with this energy equation right here. Similarly to the electric energy, we have the magnetic energy. And as you can see, this equation here is the magnetic energy of the dipole mu2 in the electromagnetic field created by the dipole 1. This is how they sum up if you have a configuration of several magnetic dipoles in three-dimensional space. What I want to point out is this equation's a little more complicated because it's a vector equation. As you can see, there's vectors here and vectors here. The B field, because it's a complicated equation, again, involves vectors. So this is the equation for a B field at point I coming from point J, the dipole of point J. If I add these two equations together, I get this one, and that is the total electromagnetic energy for a collection of charges and a collection of magnetic dipoles. So in my model, what are the electromagnetic considerations that I take into account? The one claim that I make that is unique to conventional theory is I say that the electromagnetic force is valid inside of the nucleon. And in my opinion, that's sort of hard to argue against that idea. Of course it's going to be valid inside of the nucleon. The quarks contain a magnetic moment, and all of the charge of the proton, all of the charge of the nucleon resides in the quarks. They have a spatial distribution for their location in XYZ space. I assume an equilateral triangle for simplicity. That is also what the chromodynamic force would give you when those quarks are in their lowest energy state. They don't want to be sprung out. They like to be close. There are 3 possible bonds per nucleon, 1 for each quark. After 3 bonds, the nucleon cannot bond again to a 4th nucleon. So I can't have a nucleon in space bonded to 5 or 6 different things, just 3. And this is very much like a crystal, that a crystal would only bond a certain number of times. 1 pair of quarks from 2 different nucleons is needed for a bond. And here you can see the bond. I have a quark from here and a quark from here. 2 quarks are required, 1 pair. What are the quantum considerations? So the quantum considerations are that the angular momentum of the quantum spin is properly accounted for within the energy equation. So I take my nuclide, I know the spin from the tables, and I calculate how much energy that spin has. And that is the proper thing to do. Other models do that, some models don't. I consider the ground state of the nuclide to be the lowest energy state according to the equations of electromagnetics. And as you can see, there is a minimum distance between the 2 quarks. Again, showing this figure, that is this distance from here to here, the distance between the quarks. And quantum physics also says you cannot have a static dipole moment. So if the configuration required by electromagnetics says there's a dipole moment, there's also going to be a spin. And there must be a quantum spin. So I do consider that as well. Other quantum considerations is the Pauli exclusion principle, or the states that you cannot overlap 2 nucleons. And that would be the hard repulsion as well of the nucleons. I can't overlap them. Because of that, I cannot have 2 nucleons bonded twice to each other. As you can see here, a situation like this is not allowed. I call that a doubly bonded nucleon. That is not allowed. Similarly, a quark cannot bond more than once. It cannot bond to 2 other quarks. So here, this is not allowed. So how do I determine the lowest energy configuration of these collection of quarks? I have an XYZ matrix in XYZ space. Each quark, I create a matrix, and I have the XYZ position. I also have the charge of the quark, whether it's 2/3 or minus 1/3. I also have the magnetic dipole, and I have the vector orientation of that magnetic dipole. The electromagnetic energy is calculated using the equations that I showed you and vector math. And each nuclide is itself a program that I have written in Mathematica. So I have probably several thousand nuclides that I have created. For lithium-6, for example, I have maybe 20 variations of lithium-6 to see which one is the lowest energy. These programs, once I run a nuclide and I put that into the computer memory, now I run the program to calculate the electromagnetic energy of that configuration of charges and dipoles. And from that, I can determine the binding energy. So the lowest energy configuration is, as you might guess, with as many bonds as possible. Every bond will lower that energy. So the lowest energy, as many bonds as possible. No triple bonded quarks, no double bonded nucleus. The net positive charge of the nucleus is spread out as far as possible. What that says is that you don't get a little wadded up ball of charge. And if there is a dipole moment, there is also going to be spin. I take the spin from the tables for all of them. But if I have a configuration with a strong dipole moment, I know that's not correct if the spin in the table says it's 0. Every nuclide in this paper is in its lowest energy state in accordance with the electromagnetic equations and quantums. I want to say that the charge is present at every bond. So when you look at the configurations, which I'm going to show in the next slide, you might say, oh, well, there's 2 protons right next to each other. That can't be right. And just recall, the charge is not residing in the center of the protons. The charge resides in the bond. And there's a net charge of 1/3 in every bond. The cluster model uses something called Ikeda diagrams. Excuse me if I mispronounce that. But the cluster model is very similar to my model in the way that it builds up the nuclei out of clusters. The difference is my theory is based on the electromagnetics, and I predict it based on the lowest energy magnetic configuration. Alpha segments are predominant. If the nuclei can make an alpha segment, and that is the basic building brick. Clustering results in a chain-like structure. As you can see here, this would be carbon 14, right here. I have 3 alpha particles and 2 neutrons. Here is oxygen 16. This would be oxygen 17 with the addition of a neutron. And here would be neon 21. What does my alpha particle looks like? I have, when I write these programs in Mathematica, I also have it draw a picture of what I've written. You can see the 3 quarks here. The red quarks are the up quarks. The blue quarks are the down quarks. The red are the protons. The blue are the neutrons. I'm not presuming that these are triangular neutrons or triangular protons. It's just that that's how Mathematica draws it when I ask it to draw out the nucleon. So this is a very simplified representation. It's not meant to be an accurate physical representation, but it's very easy to look at and figure out what the nuclide actually is. There are other types of segments besides the alpha particle segments, and those are, I have a tritium segment, which you can see here I have in 2 different views. I have the helium-3 segment, and I have something called an open alpha, which looks like this. Now from C12 upwards, the pattern for the lowest energy is very consistent, very similar. I have an alpha particle for every 2 neutrons and every 2 protons. I have an open alpha in the middle, and what that does is it allows the high voltage in the center of that configuration to be reduced. It offsets that voltage. It allows the positive charge to be spread out even further, and it removes the electric dipole moment, which is very important. Now, if I have an even Z, then the extra neutrons are placed in between the alpha particles, interspersed. If Z is odd, then there is a T3 segment, again, interspersed near the middle. There are 2 more considerations to take thought of if the nuclide is radioactive. If there are more protons than neutrons, then those extra protons are again interspersed between the alpha particles. And if there are more neutrons than there are alpha segments, then the neutron segments double up. And I know this is impossible to see, but we're going to talk about it anyway. Here I have an alpha N, alpha N, alpha N, all the way to here. Now I have an NN, alpha, NN, alpha, NN. So you can see there's a doubling up of the neutrons. There are no stable elements or nuclides that have the doubled up nucleons. As soon as I put 2 nucleons together, because I'm forced to in the configuration, that element becomes unstable, that isotope becomes unstable. For nuclides smaller than 12, it's hard to duplicate that pattern. So they have unusual configurations. Also, the spin energy of nuclides that are small becomes a very large percentage of their total energy. And for those 2 reasons, the smaller nuclides exhibit some unusual behavior, as you might expect. The results: the electromagnetic model has successfully modeled nuclides all the way up, both stable and unstable, all the way up to Copernicum 283. That's a big number. Only 1 variable for the best fit binding, and that is that minimum quark-to-quark distance, whereas the Weizsäcker formula has to use 5. The electromagnetic model achieves comparable results with only 1 variable. That quark-to-quark distance is 2.111 times 10 to the minus 16th meters. These calculations have been done for every figure in this presentation. And here are the results. I've got the binding energy on the top view. The red are my calculations. The blue is experiment. And I've increased a zoom in on the first 60 nuclides so you can see the details there. You can see I am able to duplicate the downward slope here. I'm able to duplicate the peaks. I'm able to do all of that with just 1 variable. And similar to Edo, I have a problem at the high end where my calculations diverge from experiment. The worst case here is about 8%. Otherwise, in here, I'm typically less than 2% or less. The unusual behavior of the smaller nuclides is predictable and understandable. Alpha half-life can be understood, and I've got the calculations for that. Haven't written the paper yet. The smaller nuclides, I have written the paper as to why they behave differently. High energy levels are explained as a difference in the configuration. Outdated objections to this model. If you have any objections to it, they are outdated, as this slide will review. It's not quantum. Yes, it is. It's not spherical. Experiment shows they're not spherical. How does this affect LENR? Well, you may think, well, gee, all that's well and good, but can you predict anything? This is the net energy when approaching two deuterium ions approaching each other. As you can see, as I come in from farther away, this is in femtometers, I get the Coulomb barrier. It peaks right up here at about 0.4 MeV, and then it quickly drops off to a cliff and becomes attracted. So from here down, you get an attractive force. I don't have time to talk about this one. Let me talk about this. This one's interesting. Why is it that the D2 to D2 reaction going to helium-4 is so rare? It happens once every 10 to the -8 compared to the other two reactions. Conventional nuclear physics cannot explain it. They say, well, helium-4 has a lower energy, therefore that should be the preferred child nucleon, but it's not. So why not? This theory can explain it. It has to do with the energy levels of the reaction. If we look at deuterium and deuterium, they will fall down into either helium-3 or a neutron, or tritium and a proton. But there's an energy well created here and an energy barrier that they cannot get over to fall down to helium-4. So there's an energy barrier. What causes that energy barrier? It's due to the magnetic bonds. Basically, the magnetic bonds would have to twist around and go into a high energy state before they can fall into the lower energy state. It has to do with the dipoles of those magnetic bonds. Thank you for your attention. Any questions? Yes.
Okay. You just made one completely wrong statement. The DD fusion reaction, the preferred result is helium-4. This is dominant by a factor with 10 to 6 at least, or 10 to 8. What your statement is based on standard model collision physics, not on the reality. No, it's wrong. It's utterly wrong.
No.
No, it's wrong.
When you have two deuterium collide, the probability is 50%. You're going to
LANR is not colliding. We have no colliding physics in LANR.
I think you're reading the wrong book there.
No.
We'll talk about that later. Sorry.
It's based on measurement of national labs, US national labs.
All right.
Yes, it's simply it's wrong. And the other thing I have to mention, are you aware that there is no magnetic attraction between two magnetic dipoles? It's only indirect over the Biot-Savart force. And you have to show this effect here in the calculation.
Okay, there is an attraction between two magnetic dipoles.
No, never.
I'm talking about Maxwell's equations. If you want to argue with Maxwell,
it's going
good luck
over.
with that.
It's going over induced charge. Only charge and magnetic field can couple. Not two magnetic fields never couple.
I'm going to agree with Maxwell on this one. Sorry.
Yeah, this is Maxwell.